Hey everyone, today we're going to put on our detective hats and solve a little puzzle. But, instead of a magnifying glass, our main tool is going to be something way more powerful, the scientific process. So, you ready? Let's dive in. And our investigation kicks off in a place that's probably pretty familiar to all of us, with one of those strange, surprising headlines you might just scroll past in your newsfeed. And there it is. Research finds taller students are better at math. I mean, that seems a little weird, right? It's specific, it says it's based on research, but something about it just doesn't quite feel right. It definitely makes you stop and think. So what does that really mean? And how would a scientist even begin to figure something like this out? See, this is the exact kind of question that kicks off a real scientific investigation. It's not about just believing a headline. It's about digging deeper and asking, how do we know what we think we know? So where do we even start? Well, to solve any puzzle, you need the right tools. And you can think of science as this awesome detective's toolkit, just filled with different ways to investigate a claim. So let's open it up and take a look at the three main tools we can use here. Okay, so you've got your controlled experiments. That's where you're trying to prove that one thing directly causes another. Then you have observational studies, where you basically just watch and record what's happening. And then there are correlational studies, which look to see if there's a relationship between two things that are just changing naturally. That last one sounds a whole lot like our headline, doesn't it? A relationship between height and math skills? Right, so to really crack this case, we have to get super clear on what a correlation actually is. I'm telling you, it's one of the most important and probably one of the most misunderstood concepts in all of science and data. And here's the definition. It's simply the degree to which two sets of data vary together. That's it. It's really that simple. It's just a measure of how much two things seem to move in sync. But, in sync can mean a few different things. So this whole idea really breaks down in three main ways. First, you can have a positive correlation. That's when one thing goes up, the other tends to go up too. Think about ice cream sales and hot weather. Then there's a negative correlation, where the exact opposite happens. Like maybe the more hours you study, the fewer hours you spend binge watching TV. And sometimes there's just no connection at all. No pattern, nothing. Okay, let's look at a classic real-world example of a positive correlation to make this stick. Here we've got some data showing years of education versus annual salary. Just by glancing at these numbers, you can already start to see a pattern taking shape, can't you? And then, when we visualize that data, oh man, the pattern becomes crystal clear. When you group the numbers like this, you see this undeniable upward trend. More years of education tends to line up with a higher salary. That is a textbook positive correlation. But, not all relationships are this neat and tidy. Correlations can be strong, where the link is super tight and predictable, or they can be weak, where the data points are kind of all over the place and the trend is a lot fuzzier. The stronger the correlation, the more confident we can be when we try to make predictions. Okay, so we've got our main tool, a solid understanding of correlation. Now, we can finally go back to that puzzling headline and crack this case once and for all. Now, let's be really clear about something. The researchers who published this, they probably did find a positive correlation. The numbers themselves were likely accurate. As student height went up, so did their math scores. So the problem wasn't with the data. It was a hidden variable that nobody was talking about, age. And there it is. That's our answer. Think about it. The study probably included students from a bunch of different grades. The taller students weren't better at math because they were tall. They were better at math because they were older. I mean, an 11th grader is almost always going to be taller and better at math than a 4th grader, right? Age was the hidden thing, the lurking variable, that was driving both height and math ability. And this brings us to the most important point of this entire explainer. Seriously, if you take away one thing, let it be this. Just because two things are correlated, it does not mean that one variable causes an effect on the other. This is the great causation trap, and learning to spot it, that's the real key to thinking like a scientist. This whole puzzle, from seeing that weird headline to uncovering the hidden variable, it's actually a perfect real-world example of the scientific process in action. So let's just quickly zoom out and look at what those formal steps actually are. I mean, this is exactly what we just walked through together, right? It all started with a question about that headline, initiating and planning. Then the researchers did their thing, performing the study and recording the data. But the crucial part, the real magic, was step 3, analyzing and interpreting that data correctly to find the hidden variable and avoid that causation trap. And then finally, you communicate what you really found. So I'll leave you with this question. Now that you have this investigator's toolkit, start looking at the world around you with these new eyes. What's a headline you've read recently that might just be a coincidence? The next time you see a claim about some surprising connection, stop and ask yourself, is it really causation, or could it just be a correlation? Thanks for digging into this with me.